Hello and what's up? Today is mixed precision training in TensorFlow, a quick discussion and Python implementation on Cypher 10 dataset. So from version 2.1 of TensorFlow, it has allowed for mixed precision training, making use of the tensor cores available in the most recent NVIDIA GPUs. So putting simply, one way to describe mixed precision training in TensorFlow could go like this: that uh, it lets you train models where the weights are of type float 32 or float 64 as usual for a reason of numeric stability, but the data, the tensor pushed between the operations have lower precision, namely 16-bit or float 16. Some of the benefits are faster model training with compatible GPU, and I will come back to this topic of what does it mean by compatible GPU here in this case with mixed precision training. And also because mixed precision use 16 bits, it will allow you to have a larger batch size. So we can use very easily 256 batch size with datasets with which if we use a similar batch size without using mixed precision, very soon we will be out of memory situation. So let's quickly go through the documentation of TensorFlow on this. And as beautiful as TensorFlow's documentation is, this mixed precision as well has been explained very, very well here. So what does it say is mixed precision is the use of both 16-bit and 32-bit floating point types in a model during training to make it run faster and use less memory. By keeping certain parts of the model in the 32-bit types for numeric stability, the model will have a lower step time and train equally as well in terms of the evaluation metrics such as accuracy. Okay, so today most models use float 32 D types, which takes 32 bits of memory. However, there are two lower precision D types, which are float 16 and B float 16, each of which takes 16 bits of memory instead. So modern accelerator can run operations faster in the 16-bit data types as they have specialized hardware to run 16-bit computations, and 16-bit D types can be read from memory faster. All right, so before understanding more about these and implementing it with Python, another concept we have to understand how this works, that is how mixed precision works, is a concept of fused multiply add. So FMA, or fused multiply add, is a technical term representing the floating point operation performed multiplication and addition in one step. This operation executes the following arithmetic calculation, which frequently shows up in various programs. Unlike separating multiplication and additional operation, it achieves higher performance and numerical precision. So this is the crux of these mixed precision training, that it has to perform the multiplication and the addition together in a single step. So the fused multiply add is a type of multiply accumulate operation. In multiply accumulate, operands, that is A, B, C, these are the operands, are multiplied and then added to an accumulator, keeping track of the running sum. Accumulator in this case is this letter R, and if fused, the whole multiply then add operation is performed with a single rounding at the end, as opposed to rounding once after the multiplication and then again after the addition. So usually this results in higher accuracy. For CPU, FMA was introduced concurrently with AVX2. FMA can be performed on scalars or on vectors packed in the way described as above. So why do we say that this was so interesting to data scientists? Well, a lot of operations in our field, dot product, matrix multiplication, convolutions, involved multiplications followed by additions, the classic concept of weighted sum. So matrix multiplication here in the space of mixed precision training actually has us leave the realm of CPUs and jump into GPUs instead, because what MPT does is make use of the newish NVIDIA tensor cores and extend FMA from scalar vectors to matrices. We will see that in a Wikipedia article a little bit more. So that's what this Wikipedia article on multiply accumulate operation says, that is fused multiply add FMA is a floating point multiply add operation. Let me zoom in a little bit. Is a floating point multiply add operation performed in one step with a single rounding. That is where an unfused multiply add would compute the product B into C, round it to n significant bits, add the result to A, and then round it back to n significant bits again. But this is not how FMA works. The FMA in infused multiply, that would compute the entire expression A plus B into C to its full precision before rounding the final result down to n significant bits. So there was a nice white paper published by NVIDIA named NVIDIA Tesla V100 GPU architecture, and they explain these whole thing a little bit more in detail with some beautiful images explaining the operation. So take a look at this image. It's here these this is a matrix, that is this image, and these three images are the input and D is the output. So how it is constructed is each tensor core operates on a 4 by 4 matrix and performs the following operation: D equal to A into B plus C. And where A, B, C, and D are 4 by 4 matrices, the matrix multiply inputs A and B are FP16, floating point 16 matrices, while the accumulation matrices C and D may be F16 or F32 matrices. And so that's how that's the main point. That is, the operation takes place on 4 by 4 matrices. Multiplication happen on 16-bit operands, while the final result could be either 16-bit or 32-bit. And they goes on to say further that the tensor cores operate on FP16 input data with FP32 accumulation. The F16 multiply result in a full precision product that is then accumulated using F32 addition with the other intermediate products for a 4 by 4 by 4 matrix, that is figure 9 here. In practice, tensor cores are used to perform much larger 2D or higher dimensional matrix operation built up from these smaller elements. So this is another important image. This is the input F16, then full precision product here, sum with F32 accumulator, convert to F32 results. Okay, the Volta. Okay. So now we will implement these TensorFlow mixed precision for our dataset of Cipher 10. Another thing that we have to remember, that we need a particular level of GPU to operate with mixed precision, and TensorFlow documentation says it clearly. Let's quickly have a look. Yes. If running this guide in Google Colab, the GPU runtime typically has P100 connected. The P100 has compute capability of 6.0 and is not expected to show a significant speed up, because NVIDIA GPUs, those with compute capability 7.0 or higher, will see the greatest performance benefit from mixed precision, because they have special hardware units called tensor cores to accelerate the float 16 matrix multiplications and convolutions. So in some cases, if you do not have a compatible and powerful GPU, actually using this has no benefit. And sometimes actually without a GPU and without the equivalently powerful GPU, your performance may slow down. So this is something to keep in mind. Okay, now let's create a small model of using the mixed precision, and we will be using Cipher 10 dataset, image dataset. TensorFlow STF, TensorFlow. So we'll name the model as mixed precision in MP model. I'm going to do keras dot sequential. Let's quickly check out the definition. It says that arguments layers, list of layers to add to the model. It's a linear stack of layers. And optionally, the first layer can receive an input shape argument. And afterwards, we do automatic shape inference. So the input shape only needs to be supplied explicitly in the first stack, and then it will do that automatically. This is identical to the following. Okay, model.add dense32. Okay. Our first layer will be layers.flatten. And we will pass input shape. There's an array, and that would be input shape is not the list, the shape. 32 by 32 by 3. Remember, we are using Cypher 10 dataset here. Here's the layers. The next would be dense. And the first argument dense text is units, which is accordingly. Okay. Sorry, this would go here. I'm passing 3000 activation ReLU. The next is also a dense layer with 1000 as unit and activation equal to ReLU. The next one is layers. I'm passing just a single unit here. And the last layer would be an activation layer with a sigmoid. Layers. Activation applies an activation function to an output, right? And that function in our case would be sigmoid, arguments activation, name of activation function to use, or alternatively a Theano or TensorFlow operation. Input shape is arbitrary. Use keyword input shape. Tuple of integers does not include the sample axis. When using the layer as the first layer in the model, output shape, same shape as input. All right, makes sense. Activation and sigmoid. Here, just note that I'm passing a data type to be explicitly float 32, and we will see why it is so much required here for this case. D type equal to float 32. Okay, that looks all right. Now, model.compile. Optimize equal to SGD. And optimizer. And our loss, because it's a 10 class Cypher dataset, so we need to have categorical cross entropy. Categorical CR. And matrix I am passing as accuracy. All right, and I can do a return model here, yeah. And now I have to, okay, so this is the important part on mixed precision training, that we have to set a policy accordingly. So if you read the documentation, mixed precision, we have already imported it, and setting D type. Okay, this is one way to do this. Policy mixed precision dot policy mixed float 16. To use mixed precision in Keras, you need to create tf.keras.mixed precision dot policy, typically referred to as a D type policy. D type policies specify the D types layer will run it. In this guide, you will construct a policy from a string mixed float 16 and set it as a global policy. This will call subsequently created layers to use mixed precision with a fix of float 16 and float 32. All right, so let's do that. Okay, our function definition is over. Now tf.keras dot mixed precision. Oh, oops, I have not imported mixed precision at the top. I think I need to do that. No, I don't need to, because I'm just using Keras here. Okay. Set global policy mixed yes. And that's the important note here, that how I'm using mixed floats 16 here and float 32 in the last layer of our method, that is keras.layer.activation. I explicitly had to mention the type float 32 because according to the official guide from TensorFlow, to use mixed precision properly, your sigmoid activation at the end of the model should be float 32, because we set the policy here as mixed float 16, and that's how we had to mention the d-type float 32 here in the within the model layers, sequential model layers. Actually, this is overwriting the policy for the last layer to float 32. Okay, let's move on here. Here are the layers. Sorry, what I'm doing here now, I have to mention the classes. I have it copied down already. All the classes of Cypher 10 dataset. These are my classes. Let's make it equal to multi-class. Cypher 10. And now I will define two variables for train and test, scaled variable actually. So x train scaled 255 and it's b equal to, that would be my x test. And I will define these x train and x test in a moment. I'm just defining the mental architecture of the model first. Okay. Actually, no, I should have pulled the data before this so that the flow looks more natural. Okay. Yeah. So I'm just pulling the data from the datasets class of TensorFlow, the Cypher 10 dataset. So that will return me a tuple x train, y train, x test, white test, df.keras.datasets dot cipher10 dot load data. Okay. And I also need to convert uh, uh, these to categorical variety. So let's do that. White train, this white train I need to convert. Let's convert the white train to categorical. So I will use a two categorical utility function of Keras. White train categorical equal to Keras dot utils dot to yes, two categorical. What does it say? Converts a class vector integers to binary class matrix, for example, to use with categorical cross entropy, and which is what we are using here at the top. Arguments y equal to class vector to be converted into a matrix, integers from 0 to num classes, and the total number of classes, d type, the data type expected by the input default is float 32. Okay, and it returns, the function will return me a binary matrix representation of the input. The classes axis is placed last. Okay, makes sense. Two categorical. And the first argument, it said that it takes a whole vector of y values. So that's what I pass. Num classes in this case 10, and d type equal to float. And I have to do the same with white test as well. White test categorical equal to keras.utils dot categorical y classes 10 and d type will be 10. And now finally, I have to run it with the GPU device. So I can make use of tf.device function. Let's see the definition. In VS Code, you have to press Control space to get the definition from the documentation. So TensorFlow.device function wrapper for the graph.device using the default graph. Args device name of function, device name or function. The device name or the function to use in the context returns a context manager that specifies the default device to use for newly created operations. Okay, let's see. I may have to change the actual device name when I run this whole code in Google Colab. But for now, I am going to use the default one, which is GPU 0. But we will change it later accordingly. Model equal to, what was a model name? ML, I think MP model. Okay, MP model. Okay. And model get fit. Okay. I need to pass the X train and Y train, and okay, let's just first X train scaled. X train scaled. I think that's right. Similarly, I have to pass Y train. Why it's not taking automatically? Why not defined it? I think I have missed X One second here. Sorry, I had to use not the scaled one here. I'm fitting it, so I needed to use the y categorical values, y test categorical, because I'm fitting it here. Y test categorical. Okay, and sorry, I'm here also another mistake. This is not x train, x test. X test scaled, Y test categorical, and now for model evaluation, I will be using the X test scaled value, and which I have defined here. Okay, just one word that why I'm using the scaled value here, and why actually I am dividing by 255 to get the scaled value. And that's because when using the image as it is and passing through a deep neural network, the computation of high numeric values may become more complex. And especially with mixed precision, this will be with the GPU, this may take a very long time if I do not scale it, and it will absolutely not become optimized. So to reduce this, we can normalize the value to ranges between 0 to 1, and in this way the numbers will be small and the computation become easier and faster. And how do I scale those values between 0 and 1? Because here I'm using the cipher 10 data set, which are of images, and as the pixel values ranges from 0 to 256, so excluding the 0th value, the range is 255. So dividing all the values by 255 will convert it to a range of between 0 and 1. And now model dot evaluate. Quickly check their definition. Evaluate. Yeah, what does it do? TensorFlow dot scalar sequential evaluate returns a loss value and matrix values for the model in test mode. Computation is done on batches, and computation is done in batches. Argument takes input data. It could be a NumPy array or a list of arrays, a TensorFlow tensor, or a list of tensor. A dict mapping input names to the corresponding arrays tensor. Okay, let's just implement it and see what it model.evaluate, and it takes the test values x test scaled, and I have to pass the y test categorical. Okay, I think with evaluate my model, my training is over. That is, I'm defining the function here. I am setting the global policy, and then I'm pulling the data of Cipher10 dataset. I am defining the classes, and here I'm scaling the xtrain and xtest data. Then I'm converting the y-test and y-train to categorical values. And finally, with device GPU 0, I am fitting the model. And then at the last step, I'm evaluating the model. So with this, all the process is over, but I want to run this entire thing in Google Colab and see. So one second, let me open Google Colab. So here I am in my Google Colab, and I'm just copy pasting the entire code here to my Google Colab, and I'm going to run it. Okay, I got an error. Let's see what this error is about. Cannot convert value mixed float 16 to a TensorFlow D type. Okay. Mixed float. Oh, I made a mistake. This extra S should not be there. Deleted that, and then Before running the actual fitting, uh, let's try it again. Okay, it's downloading the Cypher 10 dataset. And my next error is, it says cannot interpret 10 as a data type. So that is here why test categorical. Number of classes equal to 10. D type, yeah, that would be all this silly mistake. FLOAT, FLOAT. I think some of this mistake came from, I think, the VS Code IntelliSense was putting something and I just selected that. Okay, let's run it again. Okay, now it seems to have run well. And now I will be running. Oh, I will be just uncomment it and run it. It's executing. I think this fit method will take a really long time. I just wanted to see that if it's running in Google Colab well. Yeah, it has started the actual fitting process. Accuracy of, okay, these are just, okay, now I stop it because I have not included the accelerator, that is a GPU. So let's do that. Runtime, you have to select the GPU here, change runtime type, hardware accelerator GPU, standard. This one really need the highest end GPUs, that is Tesla, yes, I think V4 or something. I mean, the P100 that normally Colab gives, that will not be runnable with this notebook. So let's first see if I have got the correct GPU. NVIDIA SMI, this command will tell me what is the GPU that has, okay, I have got P100, but that is not enough for this, because remember the TensorFlow documentation clearly said that if running this guide in Google Colab, the GPU runtime typically is P100 connected, but P100 has compute capability of 6.0. But for this notebook using mixed precision, I need minimum compute capability of 7 and higher. So let's do one thing. I'm going to factory reset this Google Colab runtime. Sometime it gives the updated GPU. Factory reset runtime. Are you sure that you want to reset the runtime? Yes. And then reconnect. Let's clear this output and connected. Okay, now I'm running this again and see if I have got an updated. Oops, I again got P100. Let's try another time. Runtime, factory reset runtime, yes. And run again. No, it did not get updated. I am still at Tesla P100. So, Google Colab sometimes, because of depending on the demand and supply, uh, these GPU allocation method varies. So probably currently a lot of people are using the high-end GPU. So Google Colab, I have a Colab Pro version indeed, but still I am not getting the updated, the more powerful GPU. So okay, anyway, so I checked this code is running. It will run for a long time. Let me run in the whole collab, and if it gets completed within a reasonable time, then I will attach the output with the video. Else I'm going ahead and uploading the video in the next half an hour or so. All right, thank you very much for watching. If you like the video, you can just press the like button, And also, this is a new channel for me, but I'm going to upload quite frequently, 3 to 4 videos each week for sure. So you may think of subscribing it. Thank you again.